Hello everyone. Today in this module we are going to study about the prerequisites of Nyquist plot, which is called as polar plot. So basically what polar plot is, it is a frequency response similar to Bode plot. In Bode plot we sketch the gain versus frequency separately and then phase versus frequency. So there are two different plots in case of Bode plot. In case of Nyquist plot or polar plot, what we do is we plot magnitude as against phase when frequency omega is varied from 0 to infinity. So in basic basic concepts, if we consider polar plot and Nyquist plot, it is different from Bode plot in the sense that frequency is varied from 0 to infinity, but we are not plotting magnitude or phase with respect to frequency. We are plotting them against each other. Let me share a screen with you now, which will give you the idea how the polar plot is sketched. So the polar plot is a frequency response plot that is sketched by plotting magnitude versus phase as frequency is varied from 0 to infinity. Now, why this polar plot is called as prerequisite of Nyquist plot? Because we are going to see how the stability analysis is done with respect to polar plot, then how few parameters are located, how few parameters are calculated, like gain margin, phase margin, gain crossover frequency, phase crossover frequency, and from that how to infer whether the system is stable or not. Once we are conversant with that, then we will come across the limitation of polar plot, because of which then we have to shift to Nyquist plot, right? So first we will see, first step is to see how to sketch the polar plot. We have seen the basic, that magnitude and phase are plotted against each other versus each other, where frequency is varied from 0 to infinity. Okay, so let us look at the example. This is the example, standard example of polar plot. GSHS, open loop transfer function, is given as 10 by S. Now, as we are plotting frequency response, we only are interested in frequency part of this S. Basically, S has two parts, real and imaginary. So S can be written as sigma plus j omega. But as we are interested in only frequency part, we will substitute S is equal to j omega, ignoring sigma part, because real part has no contribution in frequency response, right? So we will ignore that sigma part and we substitute S is equal to j omega. So now what the transfer function becomes? G j omega h j omega is equal to 10 upon j omega. Then we are supposed to plot magnitude versus phase. So we need to calculate what is the magnitude expression and phase expression for the given transfer function. Okay. The magnitude is calculated as under root real part square plus imaginary part square. So that is done in this particular step, where magnitude of the numerator is only 10, right? So there is no imaginary part would be 0. So we have 10 square plus 0 square and square root of this. Okay, so now we have this, and similarly denominator can be written as 0 square plus omega square, where 0 is the real part and omega is the imaginary part. After solving this, we get the magnitude to be 10 upon omega. Similarly, phase is calculated as tan inverse of imaginary part upon real part, which we have been using in all of the techniques that we have studied. So tan inverse of, now this is okay, this part is for numerator and this part is for denominator. Numerator is only 10, right? So tan inverse of imaginary part, which is 0 upon 10, upon denominator, real part is 0 and imaginary part is omega. So tan inverse of omega by 0. Now if we consider this numerator comes out to be 0. Okay, tan inverse of 0 is 0 degrees and tan inverse of infinity is nothing but 90 degrees. Okay, so we have 0 upon 90 degrees. So that comes out to be minus 90 degrees. This minus sign corresponds to the factor which is in the denominator, right? This we do in the Bode plot as well. We studied this in Bode plot as well. Please go back and revisit this part where factors in the denominator are considered with the negative sign, right? So as for this problem, we have magnitude to be 10 by omega and phase to be minus 90 degrees. Please observe one point, that this phase in this particular problem is independent of frequency. There is no omega variable in this phase. So whatever might be the magnitude for all the frequencies, when frequency is varied from 0 to infinity, the phase is going to be minus 90 degrees and it is fixed on that, right? So now what should be the next step? When we need to plot magnitude versus phase, as omega is varied, we will vary omega from 0 to infinity. First value of omega is 0. Then we will put it in this, we will calculate the magnitude. Phase, as obvious, we get as minus 90 degrees. We keep on changing the value of omega and then we will note what is the magnitude, and corresponding phase would be minus 90 fixed for all of the values, and then we will try to plot it. Okay, so the next slide shows a table where we get to see, just a minute, we get to see all the values of omega and corresponding magnitude and phases that are calculated, right? If you have a look at this table, first column is omega. Omega is varied from 0 to infinity. Second column is magnitude, which we calculate as 10 by omega, and phase in degrees. In this particular problem, it is uniform throughout, that is minus 90 degrees. Now, when omega is 0, if we substitute omega equal to 0, this value is going to give 10 by 0, that is equal to infinity. When omega is 1, the value is 10. The omega is 10, value is 1. As we move on, we get different values, and for omega equal to infinity, we get magnitude to be 0, right? So now from this table, we are supposed to sketch the polar plot. Now what we are supposed to do, magnitude is plotted against the phase. Phase is equal to minus 90 throughout. That means we need to locate the axis in S-plane, which corresponds to minus 90 degrees. Okay, so now when we consider the next slide, we will see the sketch of the polar plot corresponding to the table. Now please have a look at this. This is S-plane, and in S-plane we have negative real axis, negative imaginary axis that corresponds to minus 90 degrees. So this angle is minus 90 degrees, and so all the points that are plotted that are on negative imaginary axis, we start with omega equal to 0, where the magnitude is infinity, and then we correspondingly plot the points across this line. The line will remain same because angle remains minus 90 degrees, and the end point is magnitude is 0 at an angle of minus 90 degrees. So basically, this problem shows that the polar plot of the given example is nothing but negative imaginary axis. Okay, so I hope it is clear now how to sketch the polar plot. The very first step is to convert, so replace S with j omega, then obtain the magnitude and phase equations or representations, and then prepare a table where omega varies from 0 to infinity and corresponding magnitude and phases are calculated, and then they are plotted against each other. Now it is not possible to plot all the points between 0 and infinity. So this is done randomly by selecting random points. We can check the angle, we can calculate the angle and magnitude, and then roughly we can sketch the polar plot. Okay, now moving on. Now the next thing that we need to revisit is, the definitions. Now these definitions are learned in Bode plot as well. Those who need revision, please revise the definitions of gain margin, phase margin, gain crossover frequency, and phase crossover frequency. Okay, what is gain margin? It is the amount of gain that can be added till the system becomes unstable. Okay, what does it mean? Suppose currently you have open loop gain to be 50, and you know that when there is a condition on value of k, as we calculated in Roots criteria also, there is certain value of k above which or below which the system becomes unstable. So suppose, for example, current value of gain is 50 and the marginal value of k above which the system is going to be unstable is say 100. So we have margin of 50 units, right? We are on 50. We can go up to 100. Till that time, the system will remain stable, and after 100, the system will become unstable. So 50 to 100, that is the margin that we have that can be added to the gain. So if we take a look at the definition, amount of open loop gain that can be added to the system till the system becomes unstable is known as gain margin. Similarly, we have phase margin. Similar to gain, we can add phase also. So how much phase can be added till the system becomes unstable is nothing but phase margin. Now, next two parameters are important, which are known as omega GC and omega PC. Sorry. So gain crossover frequency omega GC is nothing but the frequency at which gain crossover occurs. What is gain crossover? Threshold value of the magnitude or gain is nothing but 1, right? So the frequency at which the magnitude of GSHS is equal to 1 is known as omega GC. Those who have learned Bode plot, they will understand this easily. They will be able to recall what we do with omega GC and omega PC. Phase crossover frequency is nothing but frequency at which phase of GSHS is equal to plus or minus 180 degrees, right? Now, please remember these definitions. We are going to use them further. But before that, now we will see how to locate this omega GC and omega PC from polar plot. We have just now seen how to sketch a polar plot. Now, how to locate omega GC and omega PC from the polar plot. What is the use of locating omega GC and omega PC? Again, you need to refer back to the Bode plot. In Bode plot, we have seen that omega GC is useful in calculating phase margin, and from omega PC, we calculate gain margin. So if we need to calculate gain margin and phase margin, first we need to locate omega GC and omega PC in the given plot. May it be Bode plot or Nyquist plot or polar plot. So now let us take an example of polar plot. I'll just take a random example where omega GC and omega PC can be plotted. Now, suppose we consider a polar plot. Please, this is a random polar plot that I have drawn. Suppose this is a polar plot now. Now what we are supposed to do, we are supposed to mark omega GC as well as omega PC. What is the definition of omega GC? Omega GC is the frequency at which magnitude of GSHS is equal to 1. Now suppose the method is, suppose if I draw a unit circle around the origin, okay? What is the significance of this? The radius of this is 1, okay? That means all the points that lie on this unit circle has magnitude equal to 1. Now from the polar plot, which point has magnitude equal to 1? The point of intersection between the polar plot and the unit circle. This is nothing but omega GC. I hope this is clear with you. Let me revisit this. Omega GC is nothing but gain crossover frequency where magnitude of GSHS is equal to 1. We will draw a unit circle around the polar plot. On the unit circle, all the points correspond to magnitude equal to 1, right? As this is a unit circle. And the point on the polar plot